What's up, guys? Welcome back to the Jogamin. Today, I just want to show you some interesting stuff I've been working on my free time. So, if you ever watched my video about deriving the circumference of a circle using calculus, I should tell you that there is a major mistake in that. Actually, not major, but one crucial step or something like that technically is wrong, but I still have the right answer. And today's video is going to be similar to that video in that I'm going to be talking about circles and using calculus to derive an equation about the circle, which is pi r squared, being the area of a circle. Now, think about this. Actually, I'm not talking about this equation specifically. I will derive it, but in particular, I'm talking about the area of something related to a circle and its sector. The sector of a circle, the formula goes like this, which, as you can see, is very similar to the actual full circle equation for the area. And if you think about it, if you ever question why, if you ever thought of this, why the area of the circle equation is pi r squared instead of 2 pi r squared for a full circle, it's because of this 1/2 right here. And when you use calculus to derive this equation, you'll realize where this 1/2 came from and why, I don't even know what to say, but so I'll just talk about what a sector is real quick. So a sector is 2 radii at 2 points in a circle that form a portion of a circle. It's like this. This could be a sector of a circle, and there's this angle that it makes in between the 2 radii. And the area of this sector is given by this. I haven't yet derived this equation specifically. I've gotten this because getting specific angles is a little bit tricky. I might make another video on how to get the area of a sector of a circle with calculus later, but for now, let's talk about this equation. So, let's just say this is deriving the area of a circle with calculus. Alright, so first thing we have to do, let's get a graph or a drawing example of what we're drawing. Hold on. Alright, back. Anyway, so let's draw a graph representation of what we have, of what we're gonna get the area of. So, let's draw a circle on this graph. That's a pretty bad circle. Let's use shapes. Alright. So let's say we got our circle right here. It's not the best circle or graph, but let's just make do. So here's our circle. Pretend it's a line and everything, but so this is the center. Different color. Center radius. When you're getting the area of this function, well, this isn't even a function in the first place. So just like the previous time I derived the equation with a circle, we're gonna only use this half of the circle because we're not using the negative half. Okay, and we're just gonna multiply by 2 because symmetry. The full area, the absolute value of the area of the circle is basically just half the circle times 2 due to symmetry. Or maybe even we can just get the area between here and here and multiply by 4. But it's just more simpler. We just had the equation for our semicircle on top, which we do. That equation, x squared plus y squared equals r squared. But the reason why this function is this is because when you solve for y equals plus or minus square root r squared minus x squared. This plus or minus gets graphed at the same time. So you end up with a full circle, but let's say we only wanted the plus side, and we just only get the plus side of this circle, which is the positive semicircle. So that's the side we're going to be using. Alright, and we're going to say the area of a circle equals 2 times the integral, the area under this semicircle, from, let's see the bounds. This is where I got wrong in my circumference video. I wrote the bounds as 0 to pi, but if you think about it, it's not 0 to pi because we're literally getting literal coordinates, not the rotation. So this should be r and negative r, depending on your circle's radius. So if you have a circle that is centered at the origin, the bounds in which it hits the x-axis are going to be at r and negative r. Be that r is 1, then its intercepts are 1, negative 1. If r is 4, 2, then it'd be at 2. And so I think so r and negative. So we're not 0 to pi, but r to negative r. Alright. And like we said, we're going to use the positive version of this equation. So, that r squared minus x squared dx. Yeah. Alright. Let's try explaining this like an AB student. How the AB student can probably figure this out, right? So, with this in mind, let's start with solving this integral. So, where are we going to start? Well, here's the thing about this. When getting the area of this function, we draw a bigger circle. I think it's more high quality. And it's a coordinate grid. Let's just on this. Alright, so pretend that's in the middle. The thing about circles is when you're getting the area of specific points, like since I'm integrating this entire point, let's think about step by step. So let's say the integration starts at here. Like we're gonna get the area of this portion all the way from here, and then we get to get this portion and this portion and this portion and so on and so forth, right? Now if you notice, let's say we gain this point, right? If you notice at this point, you can't how to explain this. Alright, I thought about it. So, my bad for that pretty bad explanation over there, but let's say this is like the tiniest part of the circle. Right, I try to draw straight, so let's say it's a really tiny part of the circle, right? So this is how it would look like. So there's a radius to that very small point, and we're trying to get, and the area of this would be like, say this. You can draw a right triangle at this point, and pretend it's a really small triangle, so you can do this. You get the area of this triangle multiple times over right here. Like, you see how when it draws these lines, these vertical lines, as I get closer and closer circle, that line fills up this tiny gap, right? And also this area too. So what I'm saying basically is, as you go up this circle, you're getting the area of the circle, and this is one way to think about the integration of this circle, right? Like as you go on, get this portion, like you're getting small portions of the area. I know I'm probably yapping a little too hard on this, but let's just say that you got a radius and it's moving around, and as the radius moves, it's getting the area of the circle, right? This is a really bad drawing, but as you see, there's gaps here, but those gaps can be filled if you go to infinity, just like a line in some other example. So basically saying, you can relate the triangles of this circle, and it's getting the area of the radius. As it moves, it's getting the radius and area. As the radius moves up, it's getting the area because of the triangle dimension, right? So basically, I'm just saying that, what if we made a triangle that represents this situation with the circle and the radius that I drew earlier, with the angle? So what if we used, because if you tried integrating this, you're probably not gonna, you can't. There's no equation for this in general, in fact, knowledge of trig sub. This is where trig sub is like kind of comes from, right? So because of this function, like we get the area of this portion and whatnot, but it's a function of the angle. So that is what I'm trying to get at. So let's say we got this angle. Let's just be drawing this. Should be drawing this. So there's this angle right here, theta, and this portion should be the x. Wait, no, the height is the function r squared minus x squared, right? And so therefore, this side of the circle, draw a radius like here. Like this portion should be x, and this portion should be r because r is constant, and so it's just the area of the circle. Anyways, that kind of trash explanation of trig sub out the way. We can use this theta as a function to substitute for this. Now, let's see. I mean, there's many ways you can go about doing trig sub. You can use this side, or you can use tangent, or it doesn't matter which function you use. But for simplicity's sake, I'm gonna use x as my as it relates to theta. So, in relation to theta and x, the only relationship that is convenient right now would be cosine theta equals x over r, right? And remember, you have to take the derivative of theta to substitute theta. So, if the integral of cosine theta is negative sine theta equals 1 over r dx, and this multiply on that side, so you get negative r sine theta equals dx. And also, these bounds have to change along with the substitution, so we can just write cosine theta equals, now, since this is supposed to substitute for x, the bounds, right? We'll just put the bounds into here, so then now we get r over r, and cosine theta equals negative r over r. Now you get the result in cosine theta equals 1 and negative 1, and since this is a function of theta, we have to find what theta equals, cosine theta equals 1 and negative 1. And so we know, well, since our bounds are from 0 to pi, as we see in this drawing, that must mean that 1 and negative 1 are 0 and pi. I mean, because from here angle 0 is from pi, since our bounds are from r to negative r. Get it, right? So our new equation should be 2, negative r, 2 from pi to 0, and then I already subbed the negative r from here, but that's put in, I forgot d theta. Oops. So now substitute cosine theta r equals x. So substitute cosine theta r for x squared, and we get r squared minus r squared cosine theta squared times sine theta d theta. And then if you factor out the r squared, so that r squared 1 minus cosine theta squared, and square rooted, you can take out the r right here, and it'll just be just r, and then you can put it outside because r is just a constant, so you have negative 2 r squared after that. So let me just write that. Negative 2 r squared from pi to 0, and square root 1 minus r cosine squared, not writing the whole thing, right? Times sine theta, d theta, and hold on. Right. So here's this 1 minus cosine theta. You're gonna need to know a trig identity in order to realize that the square root of 1 minus cosine squared theta equals sine theta. It's derived from the Pythagoras theorem identity, whatever, of cosine squared plus sine squared equals 1. So if you solve for sine theta, you get exactly this. So once you have that, once you know that, just substitute that in, and now your resulting integral is just sine squared theta d theta. And now you're gonna ask how you can solve sine squared theta. And here's why trigs are so useful: is that you get to use like infinite amount of trig identities. You don't have to know your trig identities, but it's just so much more convenient when trig is just so. It's just there's so many things are equal to. So another thing sine squared theta equal to is 1 minus cosine theta 2 theta over 2. That's equal to sine squared theta. I'm not gonna show you why or how. It's easily solvable using one of those identities, but I'm not gonna do it. So I'm gonna erase all this. So we get negative 2r integral pi to 0, and we get sine squared, 1 minus cosine 2 theta over 2 d theta. Now, What is this equal to? Oh, it's R squared. Now, to split up the integral, so you just get negative 2 r squared multiplying the integral of 1/2 d theta pi 0 minus the integral of 1/2 cosine 2 theta pi 0 d theta. And so you do your math. This is just so much to do. Okay. So 1/2 d theta just turns to theta over 2 pi 0 minus now cosine 2 theta. That's just sine 2 theta over 2, so that should be sine 2 theta over 4 from pi 0. And then we solve, you get pi over 2, and then minus sine of 2 pi is simply 0, and 0 sine is just 0, so yeah, you get rid of that, and it's all multiplied by negative 2 r squared. Now, what happened to negative 1? I don't even know anymore. So, hold on. Oh, she-bar, I see where I got wrong. Alright, so here's where I went wrong. It's with this bound. So remember our bounds was r to negative r, right? Meaning cosine theta equals 1 and negative 1, right? Well, I didn't really care for order, and actually put negative 1. Since cosine theta equals negative 1, theta must be pi. I put pi on top when it should have been on the bottom. So let's say I did it correctly and had pi on the bottom instead of the top. Since pi is greater than 0, there should be a negative here. It's canceling that out, since I might have actually done that. So yeah, we get a double negatives, cancel that out. And now we're left with 2r squared times pi over 2. Therefore, we get pi r squared. That is part 1 of this video, without calculating negative circle. Yeah.